5, 4, 3, 2, 1, blast off. We've all seen rocket launches like this before, but do we really know how they work? How do rocket engines work? What are the connections to thermodynamics? The goal of our video today is to relate measured thrust to combustion reaction of fuel using thermodynamic principles. We have decided to work with model rockets, which utilize a solid rocket fuel, meaning that the oxidizer and fuel are stored in the same place and will not react without an igniter or heat source. Model rockets can vary based on amount of fuel and oxidizer, amount of ejection charge, and design elements related to their nozzles and aerodynamics. For the purpose of relation to this class, we have decided to focus on the thermodynamic process that is involved in the combustion reaction that creates the thrust when launching the rocket. Because thrust is directly related to mass flow, it is important for us to determine that value, which can be seen in our calculations to come. The combustion reaction is central to how a rocket engine functions and also is integral to this class. It explores the concepts of heat transfer as well as changes in energy form. The reaction goes as follows. Fuel, any substance that can burn, reacts with an oxidizer to produce products. In the case of a hydrocarbon, burning these products are usually carbon dioxide, water, and other miscellaneous gases. However, the reaction of black powder is a little different because its fuel is both carbon and sulfur, and its oxidizer is not oxygen from the atmosphere, but rather potassium nitrate. Black powder is a composite propellant, meaning the fuel and oxidizer are mixed. The powder is compressed to avoid the surface of the powder being porous to the combustion gases. This controls the rate of burning. Otherwise, there is a progressive increase of combustion. A simplified equation for the burning of black powder is as follows. When considering mass flow rate and thrust, we know that thrust is a mechanical force, and thus is related to the movement of particles, as shown in Newton's second law. We also know that the mass flow rate is equal to density times velocity times area. Substituting, we get the equation that is highlighted in blue. However, if there is a change in pressure within the system, this can create an additional force which needs to be accounted for. Since force divided by area is pressure, the force created from the pressure differential is P final minus P initial times area. The scope of this project cannot account for all the variables present in a rocket engine reaction, so we assumed we can calculate the top bounds. Further assumptions include that this is a complete reaction, that there's a Mach 1.0 at the throat of the nozzle, and that the exit pressure of the gases equals the atmospheric pressure at the exit of the nozzle. In order to model the combustion reactions that we researched, we decided to purchase a C60 Estes rocket that has no ejection charge. Mounting it on a Logger Pro force sensor as shown in the diagram, we were able to ignite the rocket engine and measure the force versus time of our C60 Estes rocket. The following two graphs represent our measured force versus time graphs for two separate trials. As we all know, impulse is force over time. Something you might be wondering is why the force versus time graphs have the shape they do. As thrust directly relates to the mass flow rate, this can be explained by looking more closely at the combustion reaction of the black powder. The gunpowder is pressed such that there is a cone shape at the nozzle, which increases the surface area available to be burned. This greater surface area available is responsible for the initial bump in the graph. As the gunpowder is consumed by the reaction and the flame front moves into the propellant, the shape of the surface area changes to the cylindrical cross-section of the propellant. As it does, the mass combusted decreases, meaning the mass flow rate and thus the thrust decreases as seen on the graph. Clearly, once the propellant is completely combusted, no more force is produced by ejecting mass. This relates back to why the black powder is compressed. By compressing it, the burn rate and therefore the thrust is more controlled. The following represents our average calculations. From the internet, we were able to obtain information about the C60 engine, including the propellant mass and the burn time. Using the average force and F equals m dot times V final, we were able to determine the exit velocity of the gas. The nozzle of model rockets have multiple parts with varying diameters. The mass ejected through the combustion chamber first goes through the convergent part of the nozzle at subsonic speeds where it accelerates. It reaches the throat, the section of the nozzle with the minimum diameter, where it experiences flow choking. This means maximum mass flow rate through the nozzle is determined by the throat area and occurs when the ejected gas's velocity is equal to the speed of sound, or Mach number 1 at the throat, so we use this for our assumption as stated earlier. However, our calculated average velocity is clearly higher than the speed of sound. This is because the next part of the nozzle, the diverging section, accelerates the gas past the speed of sound beyond Mach 1. The exit section of the nozzle is also usually designed to make the exit pressure equal to the atmospheric pressure, which reflects our other assumption. The propellant area ratio shows the relationship between the area of the propellant, the area of the nozzle, and the pressure inside the combustion chamber. As you can see from this equation, as propellant area goes up or nozzle area goes down, pressure goes up. The rate of burning, which is the distance in meters burned normal to the burning surface per second, is related to the pressure inside the combustion chamber by the equation shown. When you look at this equation, together with the relationship between thrust and mass flow rate shown earlier, you see how important nozzle design is for rocket performance. The smaller the nozzle, the higher the pressure and the greater the thrust, but the quicker fuel will be spent. If the pressure is too great and exceeds what the combustion chamber is capable of handling, the rocket will be a bomb. A larger nozzle can increase how long the fuel will burn for but decrease the thrust produced. The temperature of the gases also has to be taken into account so parts of the rocket can withstand launch. For this very reason, model rocket nozzles are usually made out of clays or ceramics. The following video shows our rocket launch at Sachem Field using a B-64 Estes rocket. We did take all necessary safety precautions. Overall, we learned how fun rockets can be. We learned about the importance of nozzle design, the impacts of rate of reaction on mass flow rate and thrust, and the ejection of hot gases from the combustion reaction. The following shows our references and citations, and thank you for watching.